For most of human history, a hurricane was a ghost. Massive weather systems packing energy to power a city for years would churn across the dark ocean and hit the coast with absolutely zero warning. Families would go to bed under clear skies, only to wake up and find their homes and streets underwater. To solve that problem, we put eyes in space, specifically 35,000 kilometers up in geostationary orbit. At that exact altitude, a satellite's speed is perfectly synchronized with the rotation of the Earth. Because both the planet and the hardware are moving at the exact same rate, the satellite effectively hovers in place. The Indian National Satellite System, or INSAT, sits in this exact type of orbit, providing a permanent, unchanging lookout over the Indian Ocean. Watching the exact same region day and night means no weather system can develop unnoticed. We track a storm's continuous path directly toward land in real time, removing the element of total surprise. But a standard camera has a major limitation. It only works when the sun is shining. At night, or even during heavily overcast days, standard satellite images are rendered entirely useless. They show up as a flat, featureless white expanse of clouds. Visible light is highly effective for telling us exactly where a storm is located. It leaves us completely blind, however, to the massive, violent energy actually building deep inside of it. To penetrate that darkness, scientists shift their focus away from light and start looking at temperature, using infrared sensors to detect invisible heat signatures. As a thundercloud grows stronger, massive vertical updrafts push moisture higher into the freezing upper atmosphere. The taller the cloud, the colder the top. Infrared technology detects this extreme cold right at the top of the cloud canopy, providing a thermal map of the system. By pinpointing those high-altitude freezing cloud taps, meteorologists calculate a storm's destructive potential in total darkness, long before it reaches the coast. Even with thermal data, we still have a problem. The thick outer layer of a storm acts like a shield, preventing infrared from answering the most critical question: how much water is actually inside? For that, we use microwave sensors. Think of them as X-ray vision for the atmosphere. Microwave frequencies pass effortlessly right through that thin outer vapor of a cloud. This lets forecasters peer directly inside. The sensor peels back the shell and maps the dense, churning pockets of liquid rain and solid ice hidden deep inside the storm's core. Seeing this internal core structure gives meteorologists the exact data they need to predict precisely how much rain will fall and how intense the winds will be at the moment of impact. Those high-altitude sentinels don't work alone. They rely on a partner network, polar orbiting satellites. These machines operate much closer to Earth. Circling from north to south, they scan narrow vertical strips of the surface as the planet spins beneath them. Because of their close proximity, these sweeps yield razor-sharp, fine-detail data. It is the exact high-resolution input required to feed global computer models. By combining the continuous stare of the high-altitude geostationary satellites with the sharp, low-altitude sweeps of the polar orbits, humanity has built an inescapable monitoring grid covering every inch of our atmosphere. When a cyclone approaches the coast, this entire system kicks into overdrive. INSAT 3DR locks onto the target in rapid scan mode, beaming down fresh data updates every 4.5 minutes. That raw, invisible space data is fired down to Earth, where it hits massive ground-based supercomputers for instant processing. This map shows the output of that calculation. The computers translate the raw microwave and infrared data into a readable, color-coded visual, with the vivid red and orange pinpointing the storm's violent core. That image provides the concrete evidence emergency teams rely on to act, allowing them to issue accurate, targeted warnings on the ground. The entire transition from an orbital sensor gathering data to a ground-level evacuation order happens in minutes, buying thousands of people the time they need to move to safety before the wind and water arrive. This is a weather map from 1968. Back in the 1960s, the very first satellites could only manage crude, grainy snapshots of daytime cloud cover, leaving forecasters to piece together the rest manually. The immediate future involves even sharper tools, like orbital lightning mappers capable of tracking electrical turbulence to predict extreme thunderstorms before they even fully form. Every forecast we check today is the result of millions of invisible measurements taken from the silence of space. It is a network built to ensure that the ghost storms of our history remain securely in the past.